So, welcome to this video on biomedical instruments. Specifically, we were looking at types of biomedical sensors, various ways in which we can classify biomedical sensors, and what is the purpose of biomedical sensors. So, what are the various quantities or physiological parameters or physiological measurable phenomena that they measure, such as pressure, temperature, and activity, displacement, so on and so forth. We'll start our discussion of resistive sensors with strain gauges as an example. Strain gauges are among the most versatile sensors that are used not just in biomedical engineering but also in various other measuring systems. But here we restrict our attention to biomedical applications of strain gauges. Usually, when you say strain gauge in general, you are referring to a foil, metal foil strain gauge. The principle of operation is the following. When you apply a pressure or a force on a metal, the dimensions of the metal changes depending on the direction in which the force is applied and the magnitude of that force. So this would cause a change in the area of the metal foil and the thickness of the metal foil. The length and the area will vary. This will cause a change in the resistance of that metal foil. It turns out that once you remove this force or the pressure, it will go back to its original state in most cases. So when the resistance changes and when we measure the voltage across that resistance, the voltage will also be changing. And it turns out that we can indeed calibrate. We can calibrate the force or pressure change to the voltage change. We can come up with a linear relationship between these two quantities. So that if I measure a change in the voltage, we can try to understand what the corresponding applied force or pressure was. That's the principle. So whatever is the change in pressure, this change in pressure, how does this change? When pressure is applied, it causes a change in the strain. So this is the fundamental principle of operation. So what we know from high school physics is that the resistance of a thin wire of say length L, an area of cross section A, and some resistivity rho, it's mentioned but the symbol is not showing up, some resistivity rho is R equal to rho L by A. For a metal, rho is a constant, but L and A will change depending on the dimensions, depending on the force or the pressure that it is taking, depending on the mechanical changes that it is undergoing. But rho will not change for a metal. The change in the resistance when the strain is applied is essentially a function of the change in the length and the change in the area plus the change in the resistivity. But just now I said that the resistivity that will not change for a metal. But this is a special case. We will discuss this special case in future slides. Now, how do you measure this change in the resistance? What is the principle? Usually, I mentioned in the previous class that we use bridge circuits for this purpose. In this case, we can use what is called as a Wheatstone bridge. We'll discuss that in a little bit. So, what is strain? Strain is essentially the ratio of change in length by the original length. Now, remember that strain itself has no dimensions. Strain is dimensionless. And since area is a function of the width and the thickness, the change in the area is essentially is a function of the change in the width and the thickness itself. And this is essentially 2 times the strain. Now, we saw what this is. In the previous slide, we saw that the change in the resistance is this R times delta L by L minus delta A by A plus delta rho by rho. Now substitute for this. Instead of delta A by A, you will find out that after some mathematics, after some algebra, you will find that this is essentially a function of the longitudinal strain and the change in the resistivity plus a new quantity, nu, 1 plus 2 nu. What is nu here? Nu is the Poisson's ratio. For those who are finding it difficult to understand what this is, I request you to go through some basic textbook or some basic material in strength of materials that will tell you what these are, because teaching these things is beyond the scope of this course, because we are interested in instrumentation and sensor and measuring systems and not mechanical principles and physics behind this. So I request you to understand what these are by working on your own. Another factor that is critical in improving our understanding of strain gauge sensors or using strain gauge sensors for measurement of physiological quantities is the so-called gauge factor. Gauge factor is essentially like gain for an amplifier. For those who are from circuit branches, you can compare gauge factor of a strain gauge to gain of an amplifier. Comparable, not exactly the same. This is essentially the change in the resistance by the original resistance divided by the strain. Now substitute the value of delta R from the previous slide into this equation. You will find out that gauge factor is essentially a function of the strain and the change in the resistivity by the original resistivity and the Poisson's ratio. And this device, strain gauge, has critical applications in several spaces. For example, if you are interested in measuring blood pressure inside the artery, so these can be made of really small, really tiny, minuscule sensitive tips that they measure intravenous pressure or intra-arterial pressure. They can be quite small, or they can be mounted on the tip of a catheter for measuring real-time changes in pressure or in force inside the body. So these are critical applications of such strain gauges in biomedical engineering. Another application can be, for example, in our lab, we use what are called as 6-component force torque sensors for measuring fingertip forces. These sensors are essentially silicon strain gauges, 3 silicon strain gauges mounted in 3 principal directions and calibrated to measure forces and moments applied in these 3 directions and about these 3 directions. These are, and they use Wheatstone bridges to convert the applied force in 3 dimensions to voltages. Of course, these are not made of metal foils, but rather they are made of silicon. And we will discuss the principles of and applications of silicon strain gauges and other strain gauges in future slides. Here are some examples, some typical values of gauge factor and temperature coefficients for different materials. What you note is nickel has an excellent gauge factor of 12, but its temperature coefficient is of the order of 10 power minus 3, whereas the temperature coefficient of constantan is of the order of 10 power minus 6. So constantan is a lot more stable when compared with, say, platinum or nickel. So if you're looking for a material, a strain gauge sensor that is required to have high temperature stability, thermal stability, then you're looking for constantan. But if you're looking for very high gauge factor, but you're not too worried about temperature sensitivity, then silicon is your best choice. Because it turns out that silicon strain gauges can have gauge factors as high as 120. And that, it turns out, is a lot. These are the so-called ultra high gauge factor strain gauges, and they are the ones that are usually used in catheter tips to measure pressure changes. These are the catheter tip pressure sensor that are used. Remember, it is not like the same material or the same metal can be used in all applications. I can give an example of each of this metal or material having a particular biomedical application. For example, constantan is frequently used to measure forces in dialysis pumps. Nickel, for example, is used to measure changes in pressure and in respiratory bands. P-type silicon strain gauges are used in catheter tip pressure sensors, and in our case, in our lab, we use it to measure fingertip forces on handheld objects, fingertip forces on handheld objects. And also, some of these devices have, for example, an array of strain gauges that measure strains or forces on a nail, for example, wearable fingernail strain gauge array that detects and measures tactile forces during object manipulation with an excellent 50 microstrain resolution, for example. Platinum, for example, is frequently used to measure loads, implantable load pins. Right? So, your decision on which material to use is dependent on the particular application that you are having in mind. Now, strain gauges also can be classified as bounded and unbounded strain gauges. Now, in unbounded strain gauges, wires are fixed between or suspended between one movable frame and one fixed frame, and pressure is applied on this diaphragm that is connected to the inner frame, which strains the wire. These wires form a Wheatstone bridge, and you can measure the voltage across the resistors of interest to measure the changes in strain. And they have low hysteresis and relatively high sensitivity, making it highly suitable for applications in catheters. Now, bounded strain gauges, in this case, the cable itself is formed into a grid and bonded with an adhesive to the foil or the diaphragm. And when the diaphragm, that this diaphragm is the sensitive part of the strain gauge. And when this diaphragm is strained, or when we apply a load onto this diaphragm, this causes a change in the resistance of the gauge. These are compact, reliable, and they are used, usually they are used in the industry. Let's look at how these are used in biomedical systems. This is a generic representation of a Wheatstone bridge. So there are four sensors: R1, R2, R3, R4 are four resistances, and you are trying to measure the output voltage. You are applying an input between R1 and R4 and R2 and R3, and you are measuring the voltage between R1 and R2 and R3 and R4. Now, depending on where you are applying, you could relate the change in the voltage to the change in the resistance. Usually, the measurements of interest are of the order of several microstrains. Very rarely we go to the range of millistrains. To measure such small changes, we need to use bridge configuration with an input voltage, in this case, which is the VEX. And if you use some circuit theory and some circuit analysis, you could come up with an expression for output voltage as R3 divided by R3 plus R4 minus R2 divided by R1 plus R2 times the input voltage. How did I come up with this? How would I come up with this? Some basic circuit analysis. Please do check how I have done this. Do check. Or if you are unable to understand, then I guess maybe you can use some standard circuit theory textbook like Administer, Electric Circuits by Administer, Sham series, or some standard electric circuit theory textbook to understand. Also remember, recall from our basic instrumentation, from our basic understanding of physics, high school physics, that a Wheatstone bridge is known to be balanced. When is a Wheatstone bridge balanced? In this case, when R1 by R2 is equal to R3 by R4. Well, in that case, if R1 by R2 is equal to R3 by R4, then the output voltage will be 0. Therefore, we replace R4 with a strain gauge, and any change in the strain in the resistance R4. How is the resistance R4 changing? Because of the strain. And how is the strain coming? Because of an applied load or force or pressure in this case. Any change in strain gauge essentially causes an imbalance in the Wheatstone bridge, and that non-zero voltage appears across the two terminals of the output. This can be connected to a standard display, CRO, or maybe we can use an analog to digital converter and then maybe display it and process it on a digital computer, for example. Another application, we have already spoken about this, is another very special set of devices is the silicon and or semiconductor strain gauges. These are high-tech devices. It turns out that P-type or P-doped piezo-resistive systems, P-type piezoresistive devices are diffused into N-type silicon of a Wheatstone bridge, and their gauge factor can be as high as 120, and that is a huge gauge factor. But recall, what is the major disadvantage of this type of sensors, strain gauges? That is, they are not thermally stable. They will work really well under thermal stability. So if you're looking for thermal stability, then you are looking for other devices. But if you're having thermal stability in your area of application, then these type of systems will have high gauge factor. They are extremely sensitive to variation in temperature. So one solution to this is to use 8 silicon elements in all the 4 arms by exposing all of them, because these can be really small, because these are made of silicon, in a really small area, in a really small volume, within which all these 8 arms are 8 elements of these 4 arms are present. It is not likely that the temperature will change by a lot. So the balance of temperature will happen. So they are used in highly sensitive biomedical sensors, such as, we gave some examples, like uh, wearable fingernail pressure sensor, or the type of sensors that we use in our lab, like the fingertip force transducers, or catheter pressure sensors, and robotics. Very often these are used to provide feedback about the force applied by a motor in a robotic device. Robotics and miniaturized systems, these are extraordinarily expensive. This is high tech, and so they are very expensive. So we have a full set of 5 silicon strain gauge based fingertip force sensors that are having a 17 diameter, so that each 17 diameter is 1.7 centimeter. So each finger can be placed on one of these sensors. So one full set of 5 sensors, when we bought way back in 2013, cost us upwards of 30 lakhs rupees. At that time, the dollar value, conversion value, was 54 rupees for every dollar. So, I mean, the one full set of 5 sensors, these cost as much as a Mercedes, simply put. They're highly expensive. So you need an application that justifies the cost. Only then you can use it. And of course, in our lab, we have such a need, because we perform fingertip force measurement to study grasping objects and situations in which we know the physics, and we are interested in understanding the brain dynamics, how the brain makes its decision, how the central nervous system makes its decision, and by performing an inverse analysis of what the brain is attempting to do by measuring the fingertip forces. So this is something that we are attempting to do in our lab. So we need such sensitivity in our lab. So we have an application, but you really need to know your application before choosing this type of sensors. So with this, we will end our conversation on strain gauges. We will continue with thermistors in the next class. Thank you very much for your attention.